Hi guys, welcome back. This is the second session of linear regression from CFA Level 2 quants. Now in the last class we covered the basic introduction to what linear regression is, dependent, independent variable, how the equation is constructed, what different elements mean. We also covered a very important note about slope coefficient as to how the absolute value of slope coefficient is not giving us an indication of the strength of relation between dependent and independent variable. But for that, we have to do the hypothesis testing to see whether the slope coefficient is statistically significant or not. And for that, we also covered two methods. One was constructing a confidence interval, and the other method was to use test statistics. Now, both these methods we covered as far as the notes go in the previous session itself. Both the methods would always give you the same result. They are just different ways of looking at the same solution. So you'll arrive at the same result in terms of rejecting the null hypothesis or failing to reject the null hypothesis, but the calculations are from a slightly different perspective in each of them. So let's move towards solving an example to understand those two methods a little more clearly. So here we have an Excel file that contains all the relevant information that we'll need for our example. Now, what I've done here is I've collected the Reliance and Sensex values for the end of day values for the last 3 months of 2019. So this is all the information from 1st October 2019 all the way till 31st December 2019. Now, in order to run a regression on this, now again, how to run it on Excel, not part of your syllabus, but it is something I think you should know anyways. Just once you have all the data entered, simply select the data tab on your Excel file, and at the very far end, you will have something by the name of data analysis. If you don't see this, you can go to files and options, and within here you have add-ins. You can add in this section from this part. So from the add-in you can enable the analysis tool pack. Once you do that, you will see data analysis. Just click on data analysis and you will find a dialog box open. Within here you have a function known as regression. All you have to do is select it and press OK, and then it would ask you to give a range of y. Now, if you remember in our equation, y was the dependent variable. In our analysis, we are taking Reliance to be the dependent variable. So I'm going to select the entire range that contains the price information of Reliance as y. Then it says to select x, which is my independent variable, which in this case I'll take as my Sensex values. After this, you have option to change the confidence level. By default, it is at 95%. We're going to leave it as it is. And just for explaining one small part, I'll check the residuals as well. All you have to do after this is press OK. And if you see, you have an entire summary of regression provided to you. Now we have firstly the regression statistics, which is R square, standard error. All of this would be covered towards the end of the class. Next we have ANOVA table, which is also going to be covered within linear regression itself. So we'll cover that again later in this particular session itself. For this example, we only need this particular information, the one that I've selected, slightly highlighted in the gray, which is the intercept term and the x variable. So basically intercept is my b0 and the x variable is my b1. I have the coefficients for them and I have the standard error for them. Let's use this information to see if we can reject our null hypothesis or not, whether the b1 value that we have, the slope coefficient, is it statistically significant or not. So let's solve it using both the approaches we covered in the previous session. Now, here on the board, I have just the relevant information we need from that example. So in the example, we had a very long regression with ANOVA table and all the details. We'll cover all of those details as and when we study them. So almost all of that content is relevant for your CFA level 2 quants. But for now, for this example, this is all the information we need. So I've rounded off a few values to fewer decimals just for the sake of simplicity. So one of the tables we had, the regression table, it gave us information about value of B0 and B1. These are the coefficients. Coefficients simply means what their absolute value is supposed to be. So right off the bat, the first thing we can do is construct an equation. Now in our case, we took Reliance share price as the dependent variable, as y. So now if my standard form of equation is y is equal to b0 plus b1 x, I can replace them with my own terminology for my specific question. So this becomes Reliance share price is equal to b0. Now value of b0 is already provided to me by the regression table itself. So we'll take it minus 1380.69 plus we have b1 again. The slope coefficient, B1 is the slope coefficient, and the value of slope coefficient is already provided to us within the regression table itself. So we'll take this 0.0714 and our x was the value of sense. So one of the first things we are able to do using this regression table is to construct the entire regression equation. Now, once we have this regression equation, we'll have a little better understanding of the analysis we are going to do. So, that note we covered in the last class, it simply said that just because this value is 0.07 doesn't mean you will consider it small or you will consider the relation between Reliance and Sensex to be irrelevant. For that, we'll have to construct, or rather we'll have to perform a hypothesis test of whether or not this value of 0.0714 is it statistically significant or not. So now let's move on to that part. So for hypothesis testing, we had two methods. One was constructing a confidence interval. Let's cover that. So if you remember from last class, the confidence interval, so it's the first approach. For confidence interval, we had a very simple equation, B1 plus minus critical value from the T distribution or the T table multiplied with the standard error of B1. Now, if you look carefully, B1 value is already there. Standard error of B1 is also provided to us. Now, this is one of those things that, for actual calculation, it is very unlikely that you'll get a question asking you to calculate this. Because for this, you'll need the entire raw data set, which is generally never provided in the question because that would make question very lengthy. So, institute again, at the end of the day, it's an exam of finance. CFA is an exam of finance. Yes, you're studying quants, but you're not giving an exam of statistics, you're giving an exam of finance. So this is the information that would generally be provided to you. So you don't need to memorize or cram any formulas of how to achieve this value. So standard error of B1 is also provided and value of B1 is provided within the regression table as well. The only thing missing is critical value of T. Now, from level 1, a lot of you must remember how to, read the T distribution. So we have a level of significance provided to us, whether it is one tail, two tail. In our case, it would be a two tail. So we'll check the level of significance in the upper row, and then on the first column on the vertical side, we have to check the degrees of freedom. Now, when you did T distribution at level 1, the degrees of freedom was taken as n minus 1. But at level 2, because we are dealing with regression, the degrees of freedom would be n minus 2. Now, the critical value of T at degrees of freedom 57 and with level of significance of 5%, let's assume 5%, that's one of the most common level of significance that is used. So at 5% level of significance in two-tailed test with 57 degrees of freedom, we don't have an outright value given, so we'll take the next best closest value that is provided to us in the distributions. So the critical value of 2, for the sake of simplicity, I am taking it to be 2. It would be very slightly higher than 2, but just for simplicity, I am taking it as 2. Now that we have all the values we need to construct our confidence intervals, we simply have to solve it. So the final equation would be something like this. It would be 0.0714 plus minus 2 multiplied with 0.00414. So you'll solve this once with the plus symbol and the other time with the minus symbol. So you should be able to get the positive and the negative, or rather the higher and the lower confidence interval. So when you solve this equation, once for the plus and once for the minus, these are the two critical values that you will get. So your confidence interval is from 0.06312 all the way till 0.07968. Now, if you go back to the notes we took in the previous session, after we have this confidence interval, the last part is to decide whether or not we reject the null or not. And if you remember, null hypothesis was saying that B1 is insignificant, or in other terms, B1 is equal to 0. So the decision rule was very simple in case of confidence interval. If this value of 0 is lying within the confidence interval, we would fail to reject the null hypothesis. But in our case, 0 does not lie within the confidence interval. So because 0 is not part of the confidence interval, we will reject the null hypothesis, which would prove that B1, the value that we have, 0.0714, this is statistically significant. So if my hypothesis was B1 is insignificant and I am rejecting this, it inherently means that I am saying value of B1 that we received from the regression, it is statistically significant. It is relevant. The movement in Sensex is relevant for explaining the movement in Reliance. So this 0.0714 is actually statistically very important in analyzing the movement of Reliance with respect to movement in Sensex value. So I hope that clarifies the first approach of confidence interval. Let's move on to the second approach. Now the second approach that we had was based on a test statistic. So second approach was to calculate a t-stat. Now for this, again, the equation was very similar to what you've already covered at level 1. It was B1 as given by the regression model. So I'll put an R here, as given by the regression model, minus B1 as assumed in the null hypothesis. This in the null hypothesis we have assumed to be 0. And this value is always already given to us as 0.0714 divided by the standard error of B1, which is 0.00414. All you have to do now is to solve this. When you solve this, you will get a value approximately close to this, so 17.2464, or just if you're taking 2 decimals for simplicity, you can take it as 17.25. Now, once we have this value, this is our t-stat for our regression distribution. Again, the last part was to take a decision. Now, if you remember from last class, based on this, our decision rule was centered around the critical values from t distribution. So at 57 degrees of freedom and at 5% level of significance in a two-tailed test, the critical values of t are plus minus 2. And the decision rule was, if my t stat lies within this range, so within the range of minus 2 all the way till plus 2. If my t stat falls within this range, I would fail to reject the null hypothesis. But in my case, again, this value is not within this range. So I will reject my null hypothesis. So this is where you'll need to have a little recap of CFA Level 1 hypothesis. Aside from that, the concept is very easy, very straightforward. As you must have observed, the decision to reject the null hypothesis or the final result that yes, B1 is statistically significant, that result was same in second and first approach. So these two approaches in exam, you would generally have the choice which one you want to use, but I would suggest knowing both of them so that, if you have any time left towards the end of the exam, knowing both approaches means you'll be able to cross-check some of your own answers to make sure that what you've selected as your answer is 100% correct. So make sure you are comfortable with both the approaches because they can be used in the exam to cross-check your answer. So that covers the entire part as to how we do the hypothesis to test the statistical significance of B1. Let's move on to the next topic. Now, the next topic that we have with us is predicting the value of y. A very small, very straightforward, very simple topic. Something that you probably already know from your school days, probably 5th or 6th class. So, how exactly do I predict the value of y? Well, the simple answer is, if you have the value of b0, b1 and x, you can simply put those values here and predict the value of y. Now, whenever we are predicting the value, we use the symbol hat. So y hat would simply come out when I have values for b0, b1 and x. Let's assume this is 5, this is 2, and predicted value of x is 10. When I input all these values, I get predicted value of y as 25. This is your basic solution. Now, if I was supposed to repeat this entire thing, a lot of you might ask, why are we studying this in CFA? We've already done this in very basic school earlier classes. Well, we are going to elaborate this. So, this is just the starting point, predicting one value of y. But normally when you will be dealing with something like share price, a client comes to you and asks, what would be the prediction for share price of a particular stock? You won't give him an exact figure, rather you'll give him a range that, we believe within 1 year, the share would be able to hit, let's say 100 to 120 rupees in terms of price. Now that range, talking in a little more CFA terms, that range is something we've already covered under multiple topics. That range is nothing but, again, a confidence interval. So for us, once we have this predicted value of y, the next step is to construct a confidence interval around this value. So again, construction of confidence interval has been the same since level 1. You have your value, the predicted value of y, plus minus critical value from t distribution, again with degrees of freedom of n minus 2, multiplied with standard error of the y. Now this value would be provided in the question itself. So you would rarely be required to calculate this because this would require a raw data set which is normally never available to you in the exam. So this value would be given to you in the question itself. T distribution, you already know how to look at it, how to pick out values from it. Y hat is nothing but 25. Once you have all these values, you simply solve this equation once with a plus sign, once with a minus sign. Let's say you get your range 20 to 30. This range or this confidence interval is going to be a little more relevant in terms of financial context. So let's say someone comes to ask you a price, you say that, yeah, we are 90% or we are 95% confident that the price of a particular stock should range between 100 to 120. So this is something similar where I would simply say that I'm 95% confident that the value of y would lie between the range of 20 to 30. Now, one of the reasons why we need this, let's say I predicted 25 and I didn't have a range. If the actual result is 24, now I have to judge whether my regression was more or less correct or not. So I need this range so that, if in reality the actual value of y falls within this range, I'll say that my prediction of 25 was more or less close to the actual value, which means my regression model was fine. But if, let's say, actual value of y comes out to be 18, I'd say that this falls far beyond my confidence levels. And at the end of the day, if it is not within my confidence interval, it means my initial regression model was not very effective, because what this predicted, 25, is far, far away from the actual value of 18. So this confidence interval serves two purposes. One is, the generic purpose of giving you a range for a thing rather than an absolute value. But the more important purpose is that if the actual results fall within this range, I can still continue using my regression, because this regression was more or less correct in predicting the outcome of y. So, small topic, predicting the value of y. Let's move on to the next topic. Next topic that we have is the ANOVA table. Now, ANOVA table is one of the most important topics that we have in the entire CFA Level 2 Quants curriculum, because there is a very good chance one of the question set or even both the question sets might contain an ANOVA table and some questions related to that particular ANOVA table. So right away, let's look at what this is. So ANOVA table would be something like this. You'll get regression and error. And then based on these two, you'll get certain information. Now, what does this regression error mean? Regression is basically talking about the elements of the dependent variable that are being covered within the regression itself. So, we have this equation y is equal to b0 plus b1x. Whatever variation in y is being covered by this element, that is my regression. Or whatever is being explained by x, that is regression, and the rest of the part which is not explained by x, something we call error. That error is not being explained by the independent variable. That error is something entirely random, entirely unexplained. That is my error portion. Now, for these, we have certain pieces of information. Firstly, we have degrees of freedom. Now, in level 2, the total degrees of freedom was n minus 1. Here also it would be n minus 1. But this n minus 1 would be split into two parts. For regression, the degrees of freedom is k. And for error, it is n minus k minus 1. Now, it is very important for you to remember these notations and these simple formula, because in the exam, we'll be creating a few more columns and it would be a big table. In the exam, one of the most asked question types is that they'll give you an ANOVA table with some information missing in it, and you simply have to fill in that information. So it is very important not just to understand what each of these elements are, but you should also be able to calculate them in case that particular information is missing in the question. So now, degrees of freedom k, in simple terms, k is the number of independent variables. Now, in case of linear regression, value of k would always be 1, because we only have x as a singular independent variable. The reason why I'm not writing it 1 here is because then I'll have to explain it again when we go to the next reading of multiple regression. So the format of ANOVA table is same for linear, multiple regression, both. That's why I'm writing the standardized notation of k. In linear regression, k would always be 1 and error term would always become n minus 2. So another reason why we have degrees of freedom n minus 2. Now, K is the number of independent variables. When we go to multiple regression, I'll cover this part again, and then we'll discuss value of K that can be 2, 3, over here I can have another term. So I could have an equation that is like B0 plus B1x plus B2z plus errata. Now over here, I am explaining why my dependent variable on the basis of z and x, which is two independent variables. This is multiple regression, which we'll cover in the next reading itself. So just for explanation, in this case, value of k would become 2. So k is nothing but the number of independent variables that I have in my regression. Now the next thing we have is the sum of squares. We have regression sum of squares and we have squared sum of errors. Now these two terms have their standardized terminology, and we also have a total. Total is simply the addition of both of these. Now in order to understand what both of these are, we need to look at a particular graph. Now normally what happens is, if you go all the way back to CFA Level 1, one of the most basic things or basic statistical tools that we use to calculate, to estimate anything, was a mean, a straightforward arithmetic mean. So if I had to predict returns for next year on the basis of last 10 years, my first method would be to simply calculate the mean of last 10 years of return. That was my most basic form of predicting anything. So if I have value of y and value of x, the most basic prediction I had of y was the mean of y. Regression then tries to enhance this by adding an explanation factor. So what regression does is, instead of saying that y is a one fixed value based on its own past data, regression is saying that maybe it is dependent on some other value, and we can explain the variation in y on the basis of that other value. So regression creates something like this, a line, where the value of y is now not just a straight mean calculation which stays the same irrespective of what the value of x is, but rather what regression now is doing is, it is explaining the value of y with reference to x. Now in reality, my actual value of y can be different from the value as predicted by the mean or as predicted by the regression. My actual value of y could be significantly different. In our example, we were talking about the share price of Reliance. Let's say based on the mean, Reliance price should be 1500. Based on the regression, it should be 1700. But in reality, the price is 2000. Now, I have to cover this distance of 1500 and 2000, and this entire distance, because this is what I can say is the deviation in certain terms. So 1500 was my prediction, and actual is 2000. I have a deviation of 500. Out of that entire deviation of 500, I can split it into two parts. One is this part, which is 200, which is the difference between what my mean was covering and what my regression is able to enhance. So my mean was only saying 1500, but based on the regression, I was able to enhance that 1500 all the way to 1700. So my prediction was enhanced slightly. Then there is this gap of, let's say, 300. If I look at this entire gap of 500, I have divided it into two parts, 200, which is covered by my regression, and 300, which is not covered by my regression. This 200 is what I refer to as explained deviation. or the explained portion, which means out of this 500, this 200 can be explained by the use of regression model itself. So if in my regression model I'm saying, Reliance price is dependent on Sensex, what I'm saying is this 200 movement in the Reliance price is being explained by Sensex itself. So this is not entirely unexplained. We have a statistical logic behind it. So this is known as explained. And this 300 is my unexplained portion, also known as residual or error. Either of the terms you can follow as you like. Now, based on this, let's understand what this is. Regression sum of squares. So basically what we do is, we have this 200. I'm going to take square of it. Now, this 200 is just at this particular point, corresponding to this value of x. I can have so many values of x at which I have a value of y being explained by the regression. Sometimes the regression value might be lower than the mean, sometimes it might be higher than the mean. So in order to make sure that the positives and negatives don't cancel each other out and we are left with a 0 at the end, we simply square them, and then after we've done the squaring, we sum all the explained portion of the part. So let's say at this point the explained deviation is 200. At this point the explained deviation is only 50. At this point the explained deviation is minus 20. What I'll do is I'll calculate the square of all of these points and add them all together. That is my regression sum of squares. So if I am to put it in an equation form, this is sum of all my deviations between my regression and mean squared. And if I talk about sum of squared errors, this is my sum of deviation of actual y. Now actual y is denoted as just y minus what is predicted by my regression square. So here also what I'm doing is, at this point this deviation is 300, I'll square it up. At some other point this deviation might be 200, I'll square that up, and I'll add all of these deviations together. That would make up sum of squared errors. And the total of these two would be the entire deviation that is being covered by my entire model. Or in other words, this total is the deviation from the mean all the way to the actual value. So we are simply bifurcating it into two parts. One is the explained portion. So whatever the mean was saying, my regression was able to enhance it a little bit. That enhancement is my explained portion, and the unexplained portion is the residual part or the error term, something that I was not able to explain on the basis of my independent variable. So I hope so far this makes sense. If you're not taking notes, I'll just suggest you pause the video and take a screenshot of this chart. Now the next part of the ANOVA table is my mean of squares. Mean of squares is simply sum of squares divided by respective degrees of freedom. So if I'm talking about regression mean square regression, this is nothing but regression sum of squares divided by k. So I'm taking sum of squares and dividing it with my respective degrees of freedom. And then I have mean squared errors, which would be sum of squared error divided by n minus k minus 1. Simply what I'm doing is I'm calculating a mean. This was the total. I'm dividing it with their respective value of degrees of freedom. So I'm simply calculating a mean value. Once I'm done with this part, the next portion is the F stat. Now, F-stat, if you remember from level 1, we had an F distribution. F-stat is based on that same concept. So it would always be a one-tailed test. The formula is very simple. Now, this is not divided into regression error. This is just a one single block. So you'll only have one value here at any given time. This would be mean square regression divided by mean square error. So you can calculate F-stat by dividing mean square regression by mean squared errors. The decision rule is simple. You reject the null hypothesis. Again, null hypothesis is going to be exactly the same, that my regression is not statistically significant, it is insignificant, and my intention is to reject it. So I would reject H null if my F-stat is greater than my critical value as observed from the F distribution or the F table. Now, F table, for all of those who might not remember exactly from level 1, a quick recap. We have numerator and denominator. We used to study the F distribution by looking at degrees of freedom of numerator and degrees of freedom of denominator. We have both given here. So degrees of freedom of numerator is k, degrees of freedom of denominator is n minus k minus 1. So we look up both of these values in the F table and we'll be able to find the critical value of F. Remember, F is always a one-tailed test. So you would, if the question says 5% level of significance, you would look at the table that says 5% in the upper tail, because it is always going to be a one-tailed test as far as we are concerned. So F-stat is another way of checking how well your regression model works. Now, a key thing to know about the F-stat. F-stat is checking how significant your entire regression model is. Now, in case of a linear regression, this will give you same result as your t distribution gave earlier when we were looking at analyzing value of B1, whether it is significant or not. The significance of F-stat would be more apparent in multiple regression, where individually we can check each slope coefficient to be significant, and then F-stat would tell us if all independent variables taken together, are they statistically significant or not. So F-stat is a judgment for the entire regression model. In case of linear regression, it is not very relevant because it gives the same result as all the other methods. So its relevance would be primarily there in case of multiple regression. Nonetheless, you calculate it by this formula, and then the rejection rule or the decision rule is very straightforward. If this F-stat is greater than the critical value from F distribution, you reject the null hypothesis. Otherwise, you fail to reject the null hypothesis. Now, we always want to be able to reject so that we can prove that yes, our regression model is statistically significant. Now, aside from this entire table, you have two other terms that are relevant. One is R square. R square is regression sum of squares divided by total sum of squares. In some cases, this denominator is also written as SST, sum of squared totals. So R square is regression sum of squares divided by total. What this means is, this is simply talking about how much of my total variation. So this is my total variation. How much of my total variation is being explained by my independent variables. So again, this is also usable for linear as well as multiple regression. What this is helping us solve is how much of my total deviation or my total variation is being explained by my independent variables. Ideally, I want this R square to be as close to 1 as possible, so that I want more and more of my changes in Y to be explained by my independent variables. The higher this value is, the better my choice of independent variables will prove to be. The last thing we have within the context of ANOVA table is the standard error of estimate. This is sort of a standard deviation of the entire regression model in terms of the error. So whenever we talk about deviation for a regression model, we are always focused on the errors, because this part is already being explained. So this deviation is already explained by the deviation in the independent variable. Whenever I'm looking at deviation of the entire regression model, my focus is on the error terms. So this is simply mean square error within under root. Now, I know a few people might think this is a little too direct, they need some explanation. I want to take you back to CFA level 1. The formula for standard deviation at level 1, we're talking back to basic statistics. This was x minus x bar square sum divided by n. Or in case of sample standard deviation, we used to have n minus 1. This, if you look over here, I can say this mean squared errors is simply sum of deviation from my regression divided by n minus k minus 1. And in case of standard deviation, I used to have a under root over the entire thing. That is exactly what I've done. So this might look, a little jarring at first that I've just directly written it. But if you logically think about it, it is nothing but the standard deviation of my regression model. And whenever I am calculating standard deviation on my regression model, I am only focused on the error terms, because the explained variation is already being covered by the deviation of independent variable itself. So this is nothing but standard deviation that you covered in level 1 applied in context of my errors. So I hope all of this makes sense. Both things are relevant for ANOVA table. You should know what each individual element means. You should also be able to calculate it. Now, for calculation, no calculation here was complicated at any part. So I don't think you should have any issues with not being able to calculate any of these, or not, finding it a little complicated. The formulas, everything is normally very straightforward. With regards to sum of squares, this is the particular column that is most often going to be given to you in the question. So, these formula, I have just written them to explain them in context of the chart we drew. But this column is something that is normally given to you in the question. Now, in the exam, one of the most common type of questions is, you have an ANOVA table, some of the information is missing. Let's say the mean value is missing, F stat is missing, R square is missing. Rest everything you have with you. Some of the questions in the entire question set might ask calculation of mean squared regression. One might ask the F stat, one might ask the value of R square. So if some information in this table is given, you should be able to calculate the entire remaining set of information. Now, just for the sake of your understanding, this entire table was also there, fully solved in the Excel file that we covered at the very start of this session. I'll link that Excel file right in the video description. I would suggest that you open it up, look it up. The ANOVA table within that Excel is exactly this. And one thing that I would request you to do is, that ANOVA table already has all the values filled in. Just imagine in that ANOVA table that you only have this much information, and try to see if you are able to calculate the entire remaining pieces of information that we have here with us. And once you calculate R square, SE, mean square errors, and the F stat, once you calculate all of these, cross-check them with the answers already there in the Excel sheet. The very last topic that we have left in the reading of linear regression are the limitations of linear regression. A very small theoretical topic, but again relevant, because now you've given level 2, that institute would it would be very pleased to directly ask you a simple question, which of the following is least likely a limitation, or something like that. So you don't want to be getting those simple questions wrong. So limitations of linear regression, we have 3 which are highlighted outright. First is relations are dynamic with respect to time. So this simply means that, one of our first assumption of linear regression was that relations are linear. Now, in some cases, it could be linear, but the relations are dynamic. They are capable of changing over time. So a relation that is linear right now might no longer stay linear after a year, after 2 years. It might turn into an exponential factor. It could turn into a fractional change. So all of those things are being covered in the first limitation, that the relations between the variables are often dynamic with respect to time. They are not going to stay the same. They change as the time passes by. Second is the assumptions. So we have very rigid assumptions. We covered 6 assumptions in the previous session. They are rigid in the sense that they might not always hold true in the real world. So, applying linear regression right away to real world is not always going to produce the most reliable and accurate results, because the linear regression inherently follows certain assumptions that might not hold true in the real world itself. Lastly, we have the fact that, if we are testing a relation between two variables which is apparent in the market, so, like we looked at Reliance and Sensex. So Reliance being a very big company, it is often going to be linked with how the Sensex moves, because Sensex is at the end of the day a judgment or a parameter to judge the entire Indian economy, or rather the more robust structures of Indian economy, because it is comprised of some of the bigger companies of various sectors and industries. So if a relation like this, you do a linear regression on Reliance and Sensex, and we find out that yes, it is statistically significant. Sensex is explaining the relation of is explaining the movement in prices of Reliance. This relation might not be usable in the market because I'm not the first one who thought of it. Entire market might be doing the same analysis and might be aware of it. So in the real market, if you want to achieve superior returns, the first thing you have to do is you need some analysis, you need some framework that is unique to you and that is not known to the outside market. So if you're just, if you're doing a regression on oil prices and oil companies, that is something that the entire market is doing anyways. So just because that regression gives you nice results and it shows that yes, what you are going on about is statistically significant, doesn't mean you will be able to achieve superior returns in the markets due to it, because everyone else in the market is also aware of those relations. So these are 3 limitations. That there could be others as well. So that covers our topic of limitations of linear regression and also completes our entire reading of linear regression. Now, before I end the session, I have a request for all of you guys. Quants at level 2, as I've said, in the first video itself, it's something that is very easy to score entire 100%. And I would really like for all of you to do that. Now, in order to do that, from the next session, we'll be starting with multiple regression. But before you go to the next video, it is my genuine suggestion and a request that the example that we looked at, Reliance Sensex, I'll have that Excel file linked below, so you can play around with that. I would also suggest, pick any 6 companies, at least 6 companies from the stock market. Pick their closing price data of any time duration you want. You can take it 1 year, you can take it 3 months, 2 months, whatever you feel comfortable with. And create sets of 2. So you pick 6 companies, you create sets of 2. So you create 3 sets of 2 companies each. Now, those 2 companies within a set, it is entirely your choice whether they have something in common, whether they are completely random, separate companies. That's entirely your call. Whatever we did in the Excel file in the class, I would request you to do that with those 3 sets. Now, 3 sets is minimum. If you are enjoying it, you can do it for more. And when you do the regression analysis, you'll get the regression table, you'll get the ANOVA table, both in the Excel file itself. Once you have that, I would request you to cross-check all the concepts that we've covered in this entire reading. So check the T stat for the slope coefficient. Check the confidence interval for the slope coefficient. Check the ANOVA table and all its information. Once you've done all of that, see if you are able to get the exact same answer that Excel was giving you outright. The reason why I'm suggesting this is, well, there are two reasons. First, a lot of students have this doubt that, what we study is often slightly disconnected from the real world. So I am giving you guys a real world example to solve. Secondly, once you solve it in this, unstructured or raw data set, once you solve the entire concept, solve the entire question from a raw data point of view or a realistic data, what you'll observe is when you move on to the questions in the books and curriculum or whatever material you're referring to, those questions straight away give you the ANOVA table. So you often don't get a context as to where the information is coming from. But once you solve these three sets of, two companies each, you will get a sense of where the data is coming from, what the data actually means. And from that point onwards, when you jump onto doing the questions and examples in your books, in your curriculum, or any other question bank that you are referring to, those questions will feel a lot easier. And I would sincerely request that you practice at least 30-40 questions from the linear regression topic before you start with multiple regression. Because I assure you, if you understand linear regression thoroughly, multiple regression is going to be a very easy topic. I mean, quants as a whole is almost done. You have nothing complicated left in quants if you understand linear regression properly. But if you aren't 100% thorough with linear regression and you straight away jump to multiple, there is a possibility that you would end up confusing yourself a little bit more than what you would want. So that's it from my side. And if you have any doubts related to any topics, I leave my contact details here and in the description below as well. So you can contact me and ask any of your queries. If you have any feedback, do share that with me as well. So that's it from my side. I hope you enjoyed it and found it informative. I'll see you in the next one. Goodbye.